So this video is going to show what kind of formulae I used for this Bosch MAP 2.5 bar sensors in my Arduino code. So this is the data sheet for the Bosch MAP sensor. So if one searches the numbers in the description for this Bosch 2.5 MAP sensor, you can get this as a PDF. So basically this is the map sensor. These are the numbers, and it looks like that. It's got 3 pins, one for the power, one for ground, and one for output. It's an analog sensor. So from the data sheet, so it's really Bosch MAP manifold absolute pressure sensor, 2.5 bar sensor. So these are the two numbers. So one really needs to, UV is basically the input voltage measured in volts, UA is an output voltage, again measured in volts, PAPS is absolute pressure measured in kilopascals. So the sensor, from the data sheet, the sensor minimum voltage is 0.4 volts, and this is for pressure. The minimum pressure that the pressure sensor can measure is 20 kilopascals or 200 millibars. Basically multiply this by 10, you get 200 millibars. So the sensor max voltage is 4.65 volts. For pressure, that's the maximum of the sensor, 250 kilopascals or 2,500 millibars. So how to derive this, because one is interested what kind of absolute pressure, that's what the sensor measures, what's the absolute pressure from this Bosch formula. So what is really the Bosch formula? So the Bosch formula from the datasheet is UA, or the output voltage is the input voltage times 0.85 divided by 230 times this P absolute pressure plus 0.0061. So this is really the Bosch formula, and one can really kind of simplify it, put the UV down there, so we get UA divided by UV is equal to 0.85 by 230 times the absolute pressure plus 0.0061, and we can basically just slightly move these around, so you can say UA divided by UV minus, so we move this around, 0.0061 is equals to 0.85 divided by 230 times P absolute pressure. Or we can really kind of simplify this and put it the other way around. 0.85 P absolute divided by 230 is equals to UA divided by UV minus 0.0061. So when we divide this is roughly 0.003697. Then basically from this one can get so PAPS times 0.003697 is equals to UA divided by UV minus 0.0061, and then in that case basically if we divide these two by this number, we can get this P absolute, which is equal to UA divided by UV overall divided by 0.003697 minus 0.0061 divided by 0.003697, or this is equal to basically this gets multiplied by this, so it's UA divided by UV times 0.003697, and if one subtract this is roughly 1.65057, so this is minus 1.65057. So in other words, the P absolute pressure is equal to basically 1 divided by 0.003697 times UA divided by UV minus 1.65057. And this is really we can actually subtract that. This is roughly 270.5847. So actually our overall formula from the Bosch's datasheet, the absolute pressure is equal to UA divided by UV times 270.5847 minus 1.65057. And this, we can use this formula. I slightly cross this, so you can use this formula really to calculate our pressure. So let's say if this is actually true. So let's say if we measure so from our data sheet, we know that 0.4 voltage output is equal to 20 kilopascal. So let's say 20 is equals to the output voltage is 0.4, and let's say the input voltage is 5 volts times 270.5847 minus 1.65057. So 20 equals to, this is 0.08 times 27.5847 minus 1.65057. So 20 equals to, so this is multiplied, it comes to 21.6468 minus 1.65057, and this is roughly 19.996 kilopascals. So we know, so basically some rounding numbers, so we know that this formula is quite correct. So we know that at 0.4 volts with 5 input we get 20 kilopascals, and with the formula actually get 20 kilopascals. So next is how was really this Bosch formula derived, or how did Bosch calculate this formula? So from the data sheet, so 2.5 bar sensor, so the input voltage UV, the output voltage UA, the absolute pressure PABS. So we know that it measure minimum 0.4 volts for 20 kilopascals or 200 millibars, and 4.65 volts for 250 or 2.5 bars or 2,500 millibars. So it's fairly simple, and it's a linear formula. So basically we have a graph like this. So here is the pressure in kilopascals, and here is the voltage on the y-axis. So what we have is we have a simple linear kind of curve, well, linear line, where we have 20 kilopascals and we have here 250 kilopascals. So when the sensor outputs 0.4 volts, we know this is 20 kilopascals and 4.65 volts for 250 kilopascals. So the simple linear model is basically y equal ax plus b. So this is your y, so these are the volts. So a is slope, that's equal to the slope, and is delta y divided by delta x. So delta y is this is delta y, so the difference in the minimum and the maximum, the maximum and the minimum, and this is delta x, the change from the maximum x to the minimum x. So the slope is basically how much does y change, or the voltage change for the change in x. So, and from this formula we can really get, and this is an intercept, so basically we just substitute those, b equals to y minus ax, so we can just have it here and calculate it. So if you really calculate the slope, so first to calculate the slope, so slope equals delta y divided by delta x, and this is equal to 4.65 volts, that's the maximum, minus the minimum, which is 0.5 volts. And because this sensor is proportional to the input voltage, we have to divide it by the input voltage. Let's say, I'll explain later if this is not 5, but in general should be 5. And so this is the delta y, and the delta x is 250 minus 20. So basically this is 4.25 divided by 5 and divided by 230. Or this is 4.25 divided by 5, 0.85 divided by 230. So next thing to calculate b, so the b is equal to y minus ax. So what we can do is we can take these two numbers, so we can say b is equal to y minus ax, or the y is 0.4, so b equals 0.4 volts divided by 5, because it's always proportional to the input voltage, minus a, we've already calculated minus a, which is 0.85 divided by 230, 0.85 divided by 230 times x, and x is 20. So 0.5 divided by 5 is 0.08, and this 0.85 times 20, it's minus 17 divided by 230, and this is approximately, when you divide those and subtract 0.08, it's 0.06087, or if one can approximate it even less, 0.0061. So just round it up to 0.0061. So we already have y, that's the linear model, y equal ax plus b. So the y is the output pressure, the output voltage divided by, because proportional to the input voltage, and this is equal to a, which we already calculated, 0.85 divided by 230, so this is 0.85 divided by 230 times BABS, that's our x, that's the kilopascals, the absolute pressure, and then we have plus 0.0061, that's our intercept, rounded up. So this is, we can just slightly change this. So UA, if you multiply UV times this equation, so we get UV times 0.85 divided by 230 PABs, and that's in kilopascals, plus 0.0061. So this is actually our formula from the datasheet, and that's how it was derived. So we can easily check this out. So let's say the output pressure, the output voltage 0.4 volts is the input, which is 5 times 0.85 divided by 230, and we know that at 0.4 volts the absolute pressure is 20 kilopascals, so multiplied by 20 plus 0.0061. So what we get, 0.4 is equal to 5 times, when we do this multiplication and division, we get 0.07391 with some rounding, plus 0.0061. And basically, if we do that, is 5 times 0.08, or equals 0.4. So we know that this formula is quite correct. So this is how to derive your own formula. Let's say this is not a 2.5 bar sensor, it could be 3 bar sensor, 1.5 sensor. So really, so you can calculate all this without a data sheet, but you need to know a few things: the input voltage, the output voltage. Well, input output, you don't really need this. This is just numbers, absolute pressure. So basically, you need to know what is the minimum voltage that the sensor measures for what pressure. So I'll give an example here for this 2.5 bar map Bosch sensor. It outputs 0.4 volts for 20 kilopascals or 200 millibars, and 4.65 volts for 250 kilopascals or 2,500 millibars, or 2.5 bars. So if you really know these numbers, it's fairly easy. It's again this plot, but we just turn it around. So this is volts here, and this is kilopascals is the pressure. So let's say this is 0.4 volts for this pressure sensor, but you could substitute this with your own values for your sensor. So this is 4.65 volts. So I know that the minimum for this sensor is 20 kilopascals and the maximum is 250 kilopascals. So again, is y equals ax plus b, and a is the slope, b is the intercept. So the intercept is y minus ax. So first we just need to calculate the slope. So slope, this is the line. So this is really the slope, delta y, and this is delta x. This is the change in x. So this is the maximum minus minimum, and this is maximum minus minimum, so delta y. So the slope is equal to delta y divided by delta x, or is equal, in that case, 250 minus 20, 250 minus 20, divided by the delta x is 4.65, 4.65 minus 0.4. And of course this output is really proportional to the input voltage, so we have to divide it by, I'll come in the next part why when this changes, what happens to this formula. So let's say the input voltage is 5 volts, so UV is 5 volts. And then what you get is 230 at the top divided by, this is 4.25 divided by 5 is 0.85, or roughly this is about 270.582. So this is our slope. So then to calculate the intercept, so let's say we take this single point, you only need one point. So we know from the formula b equals y minus ax, or b equals to y, which is 20, is 20 minus a, we already calculated 270.582, multiply by x, which is 0.4, divided by the input voltage, which is 5 volts. And this is roughly about 20 minus 270.582 times, when you divide this, is 0.08. And we roughly get 20 minus 21 point, when you multiply this, is 21.64706, or this is roughly equal to minus 1.647056. So this is our intercept. So then the model really becomes y equal to our slope, 270.582 times the output voltage divided by the input voltage minus 1.647056. And this is really our formula. So we derived, this is the absolute pressure, our slope, the input and output voltage, no, the input and output voltage, and the intercept. So we have our formula. So let's see if this is really correct. So for this particular sensor, I know, let's say, if we take one single point, again this, so if you take that one, is the same thing. So I'll take really that single point. So y is 20 kilopascals, which is equal to 270.582 times the output voltage is 0.4 volts, divided by, let's say the input voltage is 5 volts minus 1.647056. So we get 20 equals to 270.582 times, when you divide this, is 0.08 minus 1.647056. And when you multiply this and subtract it, basically 20 equals to 20. So when the sensor outputs 0.4 volts, the input is 5 volts, you can actually calculate where the output is 0.4 volts, the input is 5 volts, and you can get the absolute pressure of 20 kilopascals. So that's how you can really work it out and plug this in, this fairly simple formula in Arduino, and get your own formula. So now, what really happens if, so this is my 2.5 bar sensor, so what really happens when the input voltage is less than 5 volts? I mean, Arduino doesn't really output exact 5 volts. It could be, on my machine is 4.9, or could be 4.8 or 4.75 or whatever, 5.11, it could be something different. So what happens with this formula when the input voltage is, let's say, 4.9 volts? So the formula we already have from the previous already calculated. So y equals 27.582 times 0.4 divided by 4.9, in this case, not really 5 volts, minus 1.647056. So if you really do this, divide this, multiply, so we get, so this is for 20 kilopascals, so we know the y is 20 kilopascals, the absolute pressure, so 20, and if we do these calculations, we roughly get 20.442. So actually this is not really quite the same, and this moves even more, this is quite different. The thing is that the output voltage of the sensor is really proportional to the input voltage. So what does this mean? let's say for our formula, let's say we have 20 kilopascals output voltage, so let's say 20 equals to 270.5882 divided by 4.9 volts input voltage. If we multiply this by X minus 1.647056, why am I multiplying this by X? Because if the input voltage is not really 5 volts, this will be proportional to that, so this will be slightly smaller. If this is smaller than 5 volts, this will be really slightly smaller. So let's see how small this is. So if we do that, so we get 20 equals to 55.222 times X minus 1.647056. So we get times X minus 1.56. So if we get X out, so we get X equals to 20 plus 1.647056, the whole divided by 55.222. And when you do this, this is roughly about 0.392 volts. So basically, when the input voltage is 4.9 volts, you won't get really 0.4 output voltage in from the sensor, but you get 0.39 volts. So let's substitute. So the formula is, as we know, Y equals 270.5882 times our output voltage, which for 4.9 volts will be 0.392, and divide by 4.9 minus the same intercept, 1.647056. So Y equals to, so when we multiply and divide, that is 21.647056 minus 1.647056. You see where I'm going, so equals to 20. So when the voltage supplied is 4.9 volts and the output voltage is 0.392 volts, so then the output pressure, we know this is 20 kilopascals, so 20 kilopascals is actually exactly 20 kilopascals. So this formula actually works perfectly when the input voltage is not exactly 5 volts. So you can really do your own formula and don't really care if that works or not, simply because the output voltage of the sensor is proportional to the input voltage, basically a linear relationship. I mean, this is it. So these are the formulas that I use for my Bosch 2.5 bar sensor in my Arduino code. So hopefully this is helpful, and you can do your own calculations for your own sensor and use it as you want. So hopefully this will be useful to somebody. Please subscribe. Let me know if any comments in the comment section. I'll try to answer them. So thank you very much indeed.